Hello and welcome to this video on how you can measure power in real time in your FPGA design. Today we'll show you how to perform two different methods to monitor power in both the prototyping phase of your design using the KCU105 evaluation kit and in the design and integration phase of your end system. In each case, we'll compare a solution provided by Maxim, which can be integrated as part of your power supply solution, and the second method leverages the system monitoring feature, also known as SYSMON, found in the UltraScale FPGA itself. The right approach for you depends on your design requirements, so we'll outline the benefits of both and show you how you can implement each method in the KCU105 evaluation kit. First, let's compare the Maxim and SYSMON methods on the FPGA kit. First, SYSMON has the advantage of greater out-of-the-box accuracy. However, the Maxim solution can be calibrated to match this, and we'll show you how. Second, SYSMON requires the integration of a small design within the end design. Though this can be done with an easy-to-use wizard, the Maxim solution needs no modification. And finally, unique to the Maxim solution is that it can change the power supply voltages in real time. In short, the Maxim solution is great for a fast but coarse power measurement, while SYSMON is ideal if you prefer greater out-of-the-box accuracy and the convenience of being on-chip, hence no additional work to integrate into your end system. In terms of a solution for the end application, there are a number of things that differentiate the solutions. The first, again, is SYSMON's out-of-the-box accuracy. Secondly, a dongle is required on the Maxim solution, or the system manager could also access the current and voltage information over PM bus. For SYSMON, Vivado could be used via JTAG connection to the PC. Finally, another difference in the solution is the need for additional components on the PCB. With Maxim's in-tune regulators, current and voltage monitoring is built in. With the SYSMON solution, as you will find in the KCU105, shunt resistors and amplifiers are required to complete the solution. Maxim is here to tell you more about their approach.
So let's walk through the Maxim approach on KCU105 kit. But before we go into the details of power solutions on the board, let's take a look at the power block diagram. All the main voltage rails on this board uses Maxim power solution, which comprises of PWM controllers and regulators with PM bus interface. Max 15301 and Max 15303 are digital PWM controller and regulator respectively, with adaptive control loop compensation. Max 20751 is a PWM controller for MGT power rails. All these regulators can be monitored and controlled via Maxim's power tool GUI using the USB dongle on a Windows-based PC. The GUI allows continuous monitoring of all the main power rails on KCU105 board. Not only that, but it also allows modifying many parameter values of any of the regulators. For example, Vout value, current limit set point, sequence timing, etc. These changes can be saved permanently on the built-in non-volatile memory. The changes can be saved on an XML file for later use or reference. In addition, the GUI also allows current calibration for each rail. All the boards are loaded with the same XML file, but in certain situations, it may become necessary to calibrate specific rails to get better accuracy. The procedure to perform calibration can be found on the following link. The GUI displays the current value as a number as well as graphically. However, it must be remembered that the number comes from a high-speed 7-bit A to D converter, which is primarily designed for speed in order to activate the protection circuit. The Maxim power tool can be ordered and the GUI software can be downloaded from the following link. This is the dashboard where you see the status of each rail to the left-hand side and the sequence timing set for each rail to the right-hand side. The dashboard provides a one-glance overview of how the power system is behaving. For example, you can see the output voltage, current, switching frequency, device temperature, and all the sequence parameters on this screen. If you are interested in observing each voltage rail or making adjustment to it, You can do that by clicking on that particular tab. For example, I am going to click on the 0x0A tab. This is what it's going to look like. Here you can change any of the parameters shown in the white entry box. The device status shows all the measured values. As you can see, the output current reported by the GUI. If this parameter is very important for you to be accurate, it is recommended that we calibrate it first. To do that, let's move over to the User Calibration tab. Here we only have to worry about changing IOUT cal gain and IOUT cal offset. Before changing these, let's verify the actual current by measuring voltage across R68 at the measurement terminals. If there is discrepancy between the voltmeter reading and the GUI reading, we need to change the IOUT cal offset parameter until both the readings are close. Next, apply full expected load to this voltage rail, electronic load or load in a design in the FPGA that results in full current draw. Measure the current by measuring voltage across the same resistor. Compare it to the GUI reported reading. Adjust the IOUT cal gain on the GUI until both match. Now go back to the previous FPGA state and verify that the load current measurements match between the resistor and the GUI. If not, repeat the steps above until you are satisfied. Once complete, click on the Store User All to save the calibration data in the flash memory of the device. You can also save the configuration in an XML file by clicking on Save Configuration File. If you want to monitor Vout, Iout, temperature or Vin behavior in time, you can click on Monitor tab to see it. This is what it looks like. The Fault Set tab gives you access to fault thresholds which you can change. Remember, anytime you change something, you need to go back to the Config tab and click Store User All to save it. Lastly, PM Bus tab gives you access to all the PM Bus commands and parameters that you can control.
Thanks, Milesh. Now let's take a look at the power measurement solution leveraging SYSMON. Each UltraScale device contains a feature called System Monitor or SYSMON. SYSMON offers on-chip supply voltage and junction temperature monitoring as well as up to 17 external analog inputs. These inputs can be used to measure external supply voltages and currents. SYSMON measurements are easily accessible via JTAG, I2C and a DRP interface directly from the device's programmable logic. To measure the power being consumed by the device, you must measure both the voltage being applied to the rail and the current being consumed on each rail. Supply voltages can directly be measured on chip without external circuitry. For measuring currents, the current must first be translated to a voltage and gained up so that it can be fed into external voltage inputs of SYSMON. This can easily be done using a shunt resistor, an instrumentation or difference amplifier, as shown in the block diagram, and is implemented on key rails on Xilinx UltraScale evaluation boards. To complete the solution, we need to generate a very simple design in the UltraScale device to route the external analog inputs to the actual system monitor block. This can be done by a few clicks of the mouse with the System Management Wizard. The design we're using has 2 additional cores for demonstration purposes. A power-consuming element core consumes huge VCC current, a VCCO core to control the number of power-consuming elements. The Vivado Hardware Manager Tickle console can now be used to read back the voltages and currents from SYSMON and to control the power being consumed by the device itself. The Tickle script can be found here. So alternatively, the Teraterm window and the System Manager could be used to read back current and voltage information as shown here. But for today, let's focus on reading back via Vivado, as it will work for all end applications regardless of the System Manager chosen. Let's program the device and quickly do some power measurements. First, we'll connect to the board. At this stage, you can access SYSMON pre-configuration to view the junction temperature and core FPGA supply voltages. Now let's select to program the device. to connect to the external analog inputs and to instantiate the power consuming and VIO cores. So running the tickle script from the tickle window will cause all current, voltages and power to be reported back to the tickle console. The tickle script reports all voltages, currents and power consumed on each rail of the FPGA. Now let's engage some of the power consuming elements via VIO. Setting the VIO value to 3F should cause VCC current to increase to over 10 amps. Let's rerun our script, and here we can see the change in the power on VCC int. So now we've demonstrated two methods for quickly and easily measuring the power being consumed by an UltraScale device on an evaluation kit. By using the Maxim power supply features and tools, and by leveraging the SYSMON features for more accurate power readings. Both solutions can be implemented in the end system, but SYSMON method can be implemented regardless of the power supply vendor. Thanks for watching.